Okay, so this is the last of the lensing lectures. I want to finish the development of how we compare theory with observation, and then we'll discuss the observational status. And at the end, I'll just give a little bit of introduction to Cmb Lensing, but I don't have time for very much, but we'll see what we can do. So just to recap, for different tomographic bins, you can write down the lensing potential in terms of the Newtonian and curvature potentials, where this term here is dependent on the tomographic bin, and basically it gives you the weight, the effective weight of the potentials, the contributions to the potentials along the line of sight. So generally speaking, as you would expect, the bins which are closer to us probe the function. Oh, I'm sorry. Yes, I'm sorry. Thank you. And then you can show that, I think I had a typo in the equations just before coffee this morning, that the power spectrum of the fluctuations in this thing, I think I missed out the R squared on the bottom here. And this is the so-called Lambda approximation, which works well for L's larger than about 30. And most of the lensing signal is at much higher L's, typically around about 1,000 or so. So the Lambda approximation works extremely well. And I've put this dependence on R here, which is really a time dependence, that this thing is actually decaying with time, typically. Here's the power spectrum of the fluctuations, so defined by, so you can do this separately in terms of the potentials. For simplicity at this point, I've just taken GR and assumed that these are both the same, so we get a factor of 4 here. So this would be defined, you'll see this, you've already seen this before, and you'll no doubt see it a number of times in the subsequent lectures, that this is defined in terms of the power spectrum. This is convention dependent, so you may see it or not. And this delta function, why is there a delta function here? Not isotropy, homogeneity, right? So this is if these statistics are translation invariant, then you end up with a Dirac delta function here. So that's a completely general statement. Whether the field is Gaussian or not, it doesn't matter. Any field, as long as it's statistically homogeneous, will have a 2-point statistics that involve the Dirac delta. Okay, so this I actually defined in terms of a spherical harmonic expansion. You can either do spherical harmonic expansions, or on the flat sky, you can do this in terms of Fourier expansions. So just for simplicity, let me work with a Fourier expansion. And if you remember that kappa was d1 squared plus d2 squared times phi. In other words, I think I wrote that as phi 1 plus phi 2, 2. So if we translate that into Fourier space, so if we have k, L is the integral over theta, or over n hat, if you like, then, and similarly for phi, then KL is related very simply to phi L by being minus 1/2 L1 squared plus L2 squared times phi L, the usual. So each d by dx1 brings down a minus I L1. So that's just simply L squared over 2 times phi L. And for the shears, you can do something very similar. So gamma 1L, you may recall, so gamma 1 was phi 11 minus phi 22 over 2 times, so that becomes minus L1 squared minus L2 squared phi L. And similarly for the cross component, that becomes minus L1 L2 times phi L. So here, 4 over c squared. Is it that you can't read it or you don't agree with it? C to the 4th. Oh, yeah, you're probably right. Yeah, yeah, thank you. It's usually safest to work with c equals 1 and then it's fine. Okay, so with these tricks we can work out what the power spectrum in kappa is. So if I suppress the ij superscripts because it basically applies to anything, that it's clear from this relation that CL kappa is L to the 4 over 4 times the CL, where this is the power spectrum of the lensing potential. And this is basically a basic object that gets predicted by theory, and that will be used to relate to observation. But let's have a look also at the shear terms. It's clear that if we look at the complex gamma, so if we take the transform of gamma 1 and add in the transform of gamma 2 multiplied by I, so we're transforming the complex gamma, and if we look at the modulus of that squared, then we just get this, which is then L1 squared minus L2 squared squared over 4 plus L1 squared L2 squared, which is actually just 1/4 L1 squared plus L2 squared squared, okay, which is also L to the 4th over 4. So what we find is that the power spectrum of the complex shear field is exactly the same as the power spectrum of the convergence field. So this is true in the flat sky approximation. If you do this on all sky and you do things in spherical harmonics, then you find very slight differences at low L, but at high L, it's they're the same. Okay, so we've basically been able to deduce what the power spectrum of the shear fluctuations is in terms of the power spectrum of the lensing potential, and that then gets connected back to the theory through this equation. So we'll come back to that. I've talked about the complex gamma. We'll come back to splitting it up into the gamma 1 and the gamma 2 components in a moment. But let's just see how this is done in practice. So what one can try to do is to to estimate what the power spectrum of the shear field is, and there are methods which try to do that. So doing things in harmonic space is usually preferable because the correlation properties are nicer. But one of the complications is that the sorts of fields that are observed are quite horrible. So this is a patch of the CFHT lens survey. So it's done by multiple CCDs when this telescope is pointed at different times in different places. So some parts of the sky get observed more often than others. So the red parts get observed more often than the green parts. So there's a variation in the depth of the survey. There's also bright stars involved, and you can't measure the shapes of galaxies in the vicinity of the bright stars. So there are parts of the sky which are removed. So as you're probably aware, if you try to estimate the harmonic space statistics of a field that's not very simple, then you get all sorts of convolution effects, which I'm sure you'll hear about in some of the other courses later on. So I'm not going to go into details about that, but just to say that with a very complicated mask, then doing things in harmonic space is more challenging. So what people have tended to do so far is to work with real space coordinates, or configuration space coordinates, and then you have to relate those back to the theory. So for example, a standard way is to use what are called tangential and cross ellipticities. So these are examples of summary statistics where one takes the entire survey and one reduces it to some summary statistics which one then uses to confront with theory. And for galaxy clustering, that might be the galaxy two-point correlation function. It's a very standard old term or old statistic that people have used. So here, a common one is if you have two galaxies in the survey, that you compute the ellipticity of this galaxy in a coordinate system which is aligned along the line of the line joining the galaxies. So this component here would be the E tangential component. It's a slightly odd name because this is like the E1, but it's in a rotated system. So actually, if the galaxy was like this, it would also have a non-zero but negative E tangential. So something which is radial has a tangential ellipticity. And then the cross ellipticity would be measuring things at 45 degrees. So that's something that you can do. You measure the ellipticities in a standard coordinate frame from the survey. And when you look at the pair counts, then you rotate those using the e to the I2 2i eta transformation for a spin 2 field. So that's something which is measurable. And if you calculate two statistics, which are often called psi plus and psi minus, and they're actually weighted averages of the tangential component of one galaxy multiplied by the tangential component of the other. There might be a star in here, I'm not sure. Maybe a complex conjugate, I can't remember. And then you take the cross terms and either add them or subtract them, and that gives you two statistics. And you do this as a function of separation on the sky. You can do it as a function of tomographic bin as well. So these would be real space statistics, summary statistics that encapsulate all of the individual information that you've got for each object. Put it together into a set of summary statistics, make the comparison between the summary statistics against theory. So, yeah. How do you calculate the ellipticity? So it's a challenge if you only have a galaxy that covers a few pixels. But there are methods, either moment-based methods, as I suggested, or model-fitting ones where you know typically what the profile of a galaxy typically is, and you can try to fit. So you could fit, say, an elliptical profile with an r to the quarter de Vauquelin law, if it was an elliptical galaxy. So you could actually fit that and treat that as a statistical problem. So given the pixelized data, so you integrate over the source intensity over a pixel so that you properly account for the fact that the intensity is decaying. And then you essentially fit for the orientation and the scale length and so on. So those model fitting techniques are probably, well, they're more prevalent now than the moment-based methods. So each of them has their challenges, and there's a lot of work in making those better and showing that those can be accurate. Yeah, so the question is, in galaxy clustering, you just count the number and work out if there are more pairs at a separation than you would expect at random. Here one's doing something similar but slightly different. You are simply averaging the products of the ellipticities. So in fact, the clustering sort of doesn't matter. So it doesn't matter if the points are not distributed at random. There are some small effects in terms of the theory that come in because the sources are clustered. Those will introduce a small B mode, which I'll come to in a moment. But basically, you're just doing this. So it's similar, but not the same as doing galaxy clustering. A self-pair problem? No, because that would contribute to a zero separation, and you would not include that. So this actually introduces an interesting statistics issue, and you may discuss this with Ben Vandel later in the course. Is this a good way to do things, to reduce the map to summary statistics and then work with those? So it's relatively straightforward to do. The challenge is that what you have to be able to do is to construct a likelihood function for the data that you've got. So if this is your theory with some parameter that changes here, then you want to infer the parameter or the parameters. So in other words, find the parameters which give you an acceptable fit, if you like. So the challenge then is to work out what is the probability, if this is the truth, if the universe really has a predicted psi which is like this, what's the probability of getting this set of points? So if you only had one point, then if you assume that this error bar was Gaussian, then that would be straightforward. You could just work out the probability of it being here. This is a 1.5 sigma deviation, so you could work out that probability, that's fine. But what happens if you have two? If they're uncorrelated, it's straightforward, if you know the error bars, and if you know that they're distributed in a Gaussian way. Okay. They could also be correlated. If you know what those correlations are, then you can use a correlation matrix or a covariance matrix, which is a 2x2 matrix. So these statistics are not particularly nice statistics because they tend to move up and down together. So they're correlated. So you need to use a full covariance matrix for all of the points. And getting that covariance matrix is not trivial. Sometimes it's done by simulation, sometimes by theory. By simulations, it's challenging because you do this over very large volumes, and getting simulations of large enough volumes is challenging. If you do it theoretically, then it's quite complicated because this function here is already a two-point function, okay? This is a correlation of the ellipticities, so it's a two-point function in terms of the fields. So by the fields, I mean the phi, these phi fields, or equivalently the overdensity field. So when you look at the errors on this and the correlations of this quantity, you're correlating two-point functions, which means you need to know the four-point function. And predicting what the four-point function of density fields is very challenging once you get to a nonlinear regime. So for Gaussian fields, as they start off with, then you can compute these things fairly easily. But once you get to nonlinear physics, then the four-point function becomes challenging. So there's a lot of effort which is devoted to calculating the covariance of the observables. So it's not trivial to do the comparison with theory when you've got summary statistics. And the other question, which is also, I think, also a slightly open one, is that the way I've described it, I've said, well, these points are correlated. So we'll work out the covariance matrix, essentially the correlation matrix of the points. But we're also making another assumption there, which is that these points have a joint Gaussian distribution. Okay, and they're not necessarily jointly Gaussianly distributed. Okay, so actually doing the comparison between data and theory is not a trivial step at all. And you may discuss this more with Ben later on. So I'll propose another way of doing things in a little while, which gets around some of these issues. But let's proceed. So what we need is to we can do this calculation. We can do this from the data, get these points, but we also need the theory. And I'm just going to give you the result for this. I'll do a similar calculation for the Cmb later, which is a little bit simpler. But what you can show is that these correlation functions for separations theta are given by an integral of the convergence or the gamma power spectrum times the Bethel function. So 0 for the plus term and 4 for the negative term. So you're probably aware that if you take the two-point correlation function of a field, that it's related to the power spectrum through a Fourier transform. You've probably seen that. If you haven't, you probably will at some point. So this is the analog of this. It's basically the same idea, but these are spin 2 fields. So the relationship between the correlation function and the power spectrum is slightly different. And there are other statistics, many other statistics could do like this, and they will all end up being related to the power spectrum with some sort of kernel. Okay, so if you look to say at the gamma 1 correlation function, then you would find something in here. I think it's J0 plus J4 or something like that. So there are many two-point statistics you could use. Okay, but that gives a way to make the comparison. So as long as you can satisfy yourself that you know what the likelihood function is, then the theory is then related through the power spectrum right back to the power spectrum of the Lensing potential and hence to cosmology. Okay, so one complication to mention is that here I've described things in terms of gamma 1 and gamma 2, which are connected with the coordinate system that you use. So if this is sort of x and y, then a distortion along the x-axis corresponds to a non-zero gamma 1, but a 0 gamma 2. So it's slightly unsatisfactory to describe things in terms of quantities that depend on the coordinate system. Our inference and what we learn shouldn't depend on the coordinate system we use. And we see what the deficiencies of this are. If you look at if you do a very similar calculation to the one I did here, but instead of looking at the complex gamma, if you just look at gamma 1, then you find that the power spectrum for gamma 1 is cos squared times 2 psi L times the convergence power spectrum, where psi L is the angle of the wave vector to the x-axis. Okay, so we see that the power spectrum then depends on the mode that we're looking at. Similarly, the power spectrum for the gamma 2 component also has this dependence on the azimuthal angle of the wave vector. So it's depending on. So these are both then dependent on the axis choice. So where you put the zero of this angle is. Okay. So that's sort of slightly satisfactory. So an alternative and quite attractive way to decompose the field is into a coordinate-independent way, which are called E and B modes. And these are also common with the Cmb. But I think it's true to say that this was originally derived for lensing rather than the Cmb. So one way to do this is to consider the lensing potential, but to allow it not to be real. So as I've described it so far, then the lensing potential derived from, or the potential derived from gravitational lensing is a real quantity. But if we allowed it to have a complex component, so this would not correspond to the physics that we've described so far. This will effectively allow for curl-type terms. So our fields are determined by gradients of this term, so they're gradient-like terms, but we can allow for curl-type terms by making this complex. So these fields themselves are real fields, and so this term should be zero. If it's not, then probably something has gone wrong. So why could it be non-zero? Well, the most likely thing is that it's due to systematic effects. As I mentioned, source clustering also gives you a very small B mode. I think it's also true to say that to the extent that the Born approximation is not a good one, then you can get B modes coming from the failure of that. So these things should be very small. So one should be able to ignore these. But who knows for the systematic effects? It depends what you've done with the CCD and how you've done the data analysis. And certainly the early experiments had quite large B modes, which is probably due to poorer optics, I guess. Yeah. Okay. No, whatever the mass distribution is, it should still be described by a potential. So yeah, so not in this case. So you can show with the calculation, which I won't do, that you can you can work out the E-mode decomposition by just taking cos of 2 psi L times gamma 1 L plus sine 2 psi L times gamma 2 L, and a similar expression for the B-mode field, minus sine 2 psi L times gamma 1 L plus cos 2 psi L times gamma 2 L. So if you do this, form these combinations, then you find that the power spectrum of the EE part of this should be the convergence power spectrum, and this field should have a power spectrum which is 0. Okay. So if you're able to estimate the power spectrum of the E mode and the B mode, then that gives you a useful check on whether you've got significant systematics. If this is not consistent with 0, then you know that you have a problem. Okay, and as I say, the early surveys had significant B modes. The recent ones, it's a standard test to do, and they do pretty well. So this seems very easy to do if you can do this expansion, but as I say, this is actually quite challenging because of the horrendous mask. So there are variants of this that work in configuration space, and you can find terms that select out the B mode and the E mode. There's methods like Cosmology and various other combinations of real space coordinates, real space quantities that will tease out the E and B modes. Okay, so let's have a look at some of the results of this. So these are some of the recent results from KIDS and DES, which are KIDS and DES and the Subaru HSC survey are the state-of-the-art ones at the moment. So this is the sort of typical result that you get from lensing analysis. You have a inference of omega matter and sigma 8 are the principal things that you get out. So sigma 8 characterizes how clumpy the universe is. So that is coming from the phi terms. If you look at Poisson's equation that relates phi to delta, then that actually involves the Hubble constant and omega matter as well. So it's basically the translation from phi to the fluctuations in the density field that introduces an omega matter dependence. So for example, we could get the same lensing effect by having a very high density universe which is only slightly clumpy, or a very low density universe, but that would then have a very large relative clumpiness. So that's why you have this degeneracy that you see here. And the interesting thing about it, and this is subject of some debate about how significant this is that if you compare it with what comes out of the Cmb from Planck, is that this banana tends to lie rather low. It's true for the KIDS survey, both all of the analyses that have been done so far. For the dark energy survey, it's less obvious difference. So this S8 quantity is basically sort of collapsing things in a direction along this line here, this quantity here. So if you do that, then you find that the DES lensing is a little bit lower than Planck, but not as significantly as this one. So this is about 2.3 sigma below. So it's not really enough to be seriously concerned, but it might be an indication that the physics which is assumed in this is not right. So this is a measurement from a redshift of typically 0.5 or slightly more. The Cmb is an extrapolation from redshift of 1,000, assuming Lambda CDM. So you are basically evolving things forward and comparing what we think the linear sigma 8 would be at the present day. So if these two are really different, and this is really new physics which is coming in here, then one possibility is that those fluctuations have grown slightly more slowly than lambda CDM would predict. So you could do that, for example, by changing the dark energy properties, by allowing W not to be -1, or you could also do it by changing the gravity law so that things grew a little bit more slowly. So this is an interesting curiosity. I think it's not significant enough yet to really say that lambda CDM is being seriously challenged, but as the data gets better, and if the results tend to agree rather more with kids than they do with the dark energy survey, then that is a way to challenge lambda CDM and see if some other form of dark energy should be involved, or the gravity model is different. So, what are the challenges? I've mentioned some of the challenges of doing this. There are some more that I should tell you about. One is the uncertainty in the redshift distributions. I think I touched upon this. This is actually quite a tricky distribution to get right. And as we see, I've rubbed it off now, the connection between data and theory depends on knowing what the redshift distribution is. So that's one challenge. Another challenge is that we need the power spectrum of the phi field to do this. How well do we know it? Well, on large scales, I think we know it quite well. But on small scales, things could get complicated because of baryonic physics. So one possibility is that AGN feed energy back into the medium, and that can move the baryons around and change the overall power spectrum. And the amount by which that happens, and how much sort of outflows from collapsed objects changes the power spectrum, is a bit of an open question. And simulations show quite a big variety in predictions for how much the matter power spectrum gets messed up by complicated baryon physics on small scales. So for wave numbers larger than about unity, then there's some theoretical uncertainty, and that gives you quite a serious uncertainty in the interpretation of the lensing power spectra when L is large. So when L is of the order of 1,000 or more, then these effects become progressively more important as you go to higher L. And in order to get good signal-to-noise on the inference, then we really need to push to those high L modes. There's a lot of modes at high L. There's a lot of information there. So if you want to avoid this regime entirely and say, I'm not going to touch anything which is affected by this, then that really restricts you to some quite large-scale modes, and you just don't have the statistical power to say anything very much. So I think this is an issue that we really need to get a better understanding of, or find some way, and there are some ideas of parameterizing this and then effectively making it a nuisance parameter for the analysis. So those are the main uncertainties, I think, in all of this that I've mentioned along the way. There's the getting a good point spread function. There's getting the redshift distribution right. There's the intrinsic alignment modeling, and there's the baryon physics. So those are the main challenges to the inference of cosmology from galaxy lensing. Let me go on to just introduce you to a different way of thinking about the problem rather than using summary statistics, and that is to approach the problem in a different way, where you use as much of the data as you can. And this is the approach that we're pursuing. And that is to treat the problem as a hierarchical model. So let me give you just a flavor of this in its sort of simplest incarnation. If we think about the problem that we're trying to solve, then what we really want to get at the end of it, from a Bayesian perspective, we want a posterior, which is the probability of the parameters of the model. And in this case, what I'm really thinking about is the cosmological parameters, omega matter, sigma 8, and so on, given the data that we've collected. Okay, so that's the posterior. And from a Bayesian perspective, that's if you know that, then you've analyzed the experiment and you've got everything out of it. But the data model has a lot of other uncertainties in it as well. So if you think about looking at a shear map of the sky, I mentioned that the estimates of the shear on a galaxy by galaxy basis are very noisy. So what we actually measure is a very noisy estimate of the shear field. So there's another parameter or set of parameters in the problem, which is the true shear field. So the true map. So you can write this distribution as just using the ordinary rules of probability as the joint probability of the parameters and the map, and that may be a number of different maps for different tomographic bins, but let me just call it generically the map. So just the usual marginalization rules of probability, that if I integrate the probability of the parameters and the map over the map, then I just get the probability of the parameters. So this is actually the first step of a hierarchical model where we have essentially some so-called latent variables, which are the values of the true shear field. So the question is, can we calculate this thing? So what do I mean by integrating over the map? Well, if we pixelize the sky in some small pixels, then the true value of the shear, the two numbers, gamma 1 and gamma 2, would be two parameters of the data model. So we have two parameters for every pixel in the map. So this corresponds to simulated data where we have something like 100,000 of these map parameters. And what we can do is to we don't have an analytic expression for this joint distribution, but we can sample from it using very high-dimensional sampling techniques, Hamiltonian Monte Carlo or Gibbs sampling. So you may hear about some of these techniques from Ben later on. So these can be something like million-dimensional parameter spaces, but we can sample from those. So if we do that, then this is what we find. So here is an example. This is the gamma 1 simulated map. This is a toy example. We've got two tomographic bins, but just concentrate on one of them. We add a lot of noise because of the shape noise, and we mask out some regions because of bright stars. So those are the data. And then what we can do is to sample from these. And the nice thing about this is that we can write this using Bayes' theorem as the proportional to the probability of the data given the parameters and the map times the probability of the parameters and the map. And then marginalize over the map. So this quantity, these quantities, some of them we know. So the first point is that the probability of the data given the parameters and the map, actually this depends only on the map, because these are the data are the noisy estimates of the shear, and those depend only on what the true values of the shear are in the pixel. It doesn't depend directly on the parameters. This is just shape noise. So that's the probability of the data given the map, and this one we can subdivide into the probability of the map given the cosmological parameters times a prior on the cosmological parameters, and then marginalize over the map. So this is quite nice because we split the data model into a hierarchy of terms. This is basically to do with shape noise. Just the fact that ellipticities are random and their variation is quite large. The probability of getting a map given the cosmological parameters, well, that's theory. Okay, so the statistical properties of the map are determined by the cosmological parameters. And this part here is just a prior. Okay. So the point is that by doing this, splitting the problem up like this, then we divide it into probability distributions that we have a chance of knowing. So unlike the case of using summary statistics where you don't really know what those probability distributions are, then here you subdivide the problem into probability distributions that in principle we do know. And the one which is hardest is this one. And I won't go into details, but that's the most challenging. The other challenging thing about this is that this is a very high dimensional space. So we're searching 1 million parameters. So if you look at the third panel here, then what you'll see is that we can draw samples from the map and the cosmology simultaneously. So you see this in this movie. Each frame corresponds to one draw from the sample from this joint distribution, just showing the map bits. The last term shows you the variance. So let me just show you again. Yeah, okay. So these are all individual samples of the true shear map given the observed noisy one. So there are many maps, shear maps, true shear maps, which are consistent with the data because it's noisy. And this process of sampling will draw out the possible maps with the right probabilities. Okay, so you see that many features are quite stable. There's a high shear region here. And you also get some information inside the masked regions because you're also assuming the power spectrum. So you can extrapolate into these regions. So the variance in these masked regions is higher, but it's not infinite. You get some information there as well. So the nice advantage of this approach is also that I mentioned that it was really difficult to do things in harmonic space because of the very horrible mask that you have. Actually, with this approach, the mask is trivial because in this probability of the data given the map, this is a joint probability of a lot of pixel values. So there are some pixels which are masked out, and all you do is simply give those pixels an infinite variance. So it's very trivial to include the mask into this sort of approach. The challenge is the sampling, and the challenge is doing this as precisely as possible. But in principle, it's the right way to do it. I mean, this gives you a principled Bayesian way of inferring the parameters. And you get out posteriors, which I won't show you them, but they're actually, well, I will show you some of them. These are the maps from CFHT lens from the 4 fields of CFHT lens. So these are the average maps. So taking those sampled maps and then averaging them. So that gives you something, information on the projected mass distribution. But we also get the E and B modes power spectra out of this. So this is, again, done in harmonic space. So what we get out is the entire joint distribution of all of these quantities all at once. So if you've got a big enough selection of samples from the posterior, you've basically got all of the information that's present in the experiment, and you can then use these to do any further analysis that you might want to do. You can get the B modes. So this is from simulated data. The B modes should be very small. The shot noise level is at the top here. So we recover the B modes even though it's 2 orders of magnitude below the shot noise level. So these are very powerful techniques to use. I've got 10 minutes left. I'm just wondering whether it's worth saying something about Cmb lensing or whether it's worth just stopping here. I probably won't go through any more derivations, but just to say that you can generalize these ideas to CMB lensing. Just perhaps say that what are the differences and what are the advantages and disadvantages? Well, so one advantage is that you avoid some of the difficulties that we have with galaxy-galaxy lensing, in that shape noise is not an issue. The CMB is a continuous field, so the effect that one's looking for is not so much the changes in the shape of individual objects, but it's actually the movement of temperature across the sky. So the temperature map simply gets distorted by a distortion pattern. And I think along the way to deriving the lensing potential, I had an expression for the bending angle, and that's the one that would be used for CMB lensing. One advantage is that it's a very high redshift, so it includes a large amount of lensing. So it's a relatively large signal compared with lower redshift galaxy lensing. The disadvantage is that you only have one. You have one source surface. For galaxy lensing, for Euclid and LSST, we will probably have something like 10 tomographic bins with depth information as well. So for the CMB, you only have one, so you don't probe the depth so much, and you also have less data, fewer data. You can do very similar things to the calculations that I've done here. I was going to go through a calculation to show you what the potential for the CMB fluctuations looks like. It's very similar to what we did before. Simpler, in fact, because you don't need to integrate over the redshift distribution, because it's basically at a fixed redshift. And that probes, what it does is to probe typically the mass distribution round about a redshift of 2, the contributions from different redshifts to the overall power spectrum of the potential at the last scattering surface is shown here, and the bulk of the effect is coming from redshift 2. It's a bit dependent on which mode you look at, so it depends which mode you look at, but it's probing slightly higher redshift. So one advantage of that is that the field is rather more linear at higher redshift, so one needs to worry less about the nonlinear evolution of the density field at high redshift. So unless you look at rather large L, so this is L of 1,000 is here. So around here, the nonlinear effects are beginning to be a bit more important, but it's less of an issue. If you're interested in CMB lensing, then this paper by Anthony Lewis and Anthony Challoner in 2006 is a wonderful resource. This has been measured, so I won't go into details about how, but there's a couple of different ways. But this is from the latest Planck lensing paper. So the predictions from Lambda CDM are the solid line, and these are the measurements from Planck and also from some of the smaller angle experiments. So I think it's something like a 40 or 50 sigma detection of the lensing effect. And this is the best or most probable estimate of the deflection angle, the magnitude of the deflection angle across the sky. This is basically a very noisy but map, but which is where the noise is uncorrelated with the signal. So this is telling you about the projected mass distribution along the line of sight to the CMB. So it has many advantages over galaxy lensing. You can actually use it in combination with galaxy lensing to improve on some of the understandings of intrinsic alignments, which clearly don't apply here. If you do this with polarized data, that's also a very interesting thing to do, because as you know, V modes are a signature of primordial gravitational waves. So in that case, you have to take into account the lensing, because one of the effects of lensing is to change E modes, which are present in the, so this is CMB E modes. So those CMB E modes in the polarized light. So there's a polarization E modes, nothing to do with lensing E modes. Those polarization E modes get changed they get into B modes by lensing. So on large angulars, on large L scales, then the dominant B modes are caused by this. So you need to either de-lens the CMB if you're going to look for the B modes, or try to model the the B modes that come from lensing as well as the primordial ones. Okay, so there's lots of interesting physics, and there's some of the statistical problems of analyzing lensing in the Cmb modes are still being developed. So there's interesting work to be done in trying to understand Cmb lensing in a Bayesian way. Okay, let me stop there, but I'll take any questions that you have. Probably. Yeah, I mean, I think one's interested in the matter power spectrum only, so it's a simpler problem than galaxy clustering in that one doesn't need to worry about galaxy bias or anything. So really, one should just use the best method for getting the matter power spectrum. So HaloFit is a pretty good place to start. I think the main concern really is, as I mentioned, is the non-baryonic physics effects. So that's a subject which is still developing, and I think our understanding of those processes is still in flux. But it could well be that there are methods like Alex Mead has done some work on this, where you model some of the baryonic physics on small scales, and people do some fitting to the simulations that include some of these effects. So I would say yes, but just be aware that baryons may mess things up on small scales. Okay, so if there's nothing else, then let's take a break, I think, until 3:15.